Hello everyone. So I'm so sorry. So I had a problem with Zoom where I couldn't start the meeting for some reason, or like I opened the wrong Zoom meeting, something like that. So let me just wait like maybe like 30 seconds and then we'll start today's class. If possible, I could also extend today's class to so it lasts like or it ends like 3 minutes later to make up for lost time. All right. So today we'll be talking about intermediate geometry problems in AMC8. So one of the things to consider in AMC8 is that generally you're solving problems area and whatnot, right? So continuing on from last week, we'll look at the first problem of the day, which is problem 19. So we have a triangle with vertices A, B, and C that's plotted on the 6x5 grid. So what fraction of the grid is covered by the triangle? So when we look at a problem like this, what fraction of the grid is covered by the triangle, we automatically think of area, right? So if we can find the area of ABC and divide it by the area of the entire grid, then we're basically done, right? That's what we want to find. So now we want to find the area of ABC. By the way, putting brackets around like the name of a triangle signifies area. So how would we find this? Well, there are numerous ways of finding an area, like given the coordinates, right? So you might have heard of shoelace, right? Shoelace is a way where you have a formula and you have basically some coordinates and you want to find the area of the triangle. So that's one way you could approach this problem. Another way, alternatively, is basically applying what we learned from last week, which is using complementary area. So essentially, how we would do this is where we find like the area of this rectangle in blue that I just highlighted, that would be 3x4, so that's 12, minus the area of these three triangles. So if we take the area of the rectangle and we subtract the area of the three triangles, then we have the area of like the inner triangle ABC, which is what we're trying to find. So let's first solve this problem using this method. So and then I'll talk about Shoelace theorem, since it might be like the first time you heard about this. So we basically take the area of this blue rectangle, that's 12, minus area of this larger blue triangle, that's 2x4. So that would be 2 times 4, 8/2, minus 4, minus 1/3. So that would be 3/2. And then minus 3/2 again. Since the area of this triangle is 1/3, divide by 2, base times height, divide by 2, right? So then we just get 12 minus 4, and then minus 3. So then we would get 5. So what's the area of the whole rectangle? So now we have found ABC, right? That's 5. So now we just have to find the area of the whole rectangle and then we're done. So we know that the rectangle is a 6x5 grid. So then we just get 5/30, and that's equal to 6/5. Or sorry, 1/6. 1/6, yes. So that's our answer using complementary area. So now let's look at what exactly is Shoelace theorem. So the Shoelace theorem is this theorem such that if you have a polygon P and it has vertices A1, B1, A2, B2, all the way to AN, BN, where the vertices or the vertices are listed in clockwise order, then the area of P, the polygon, is 1/2 times the absolute value of A1, B2 plus A2, B3 all the way to AN, B1 minus B1, A2 plus B2, A3 ... BN, A1. So the reason why it's called the Shoelace theorem is because if you were to do this, right? So you would get something that looks like a shoelace. So let me just like head over to images to show you what it looks like. So essentially it looks like this. So let's say you have these three coordinates. They're x1, y1, x2, y2, and x3, y3 respectively. They're the three vertices or the 3 points of a triangle. So how do you apply shoelace? You would then take these three coordinates, write them like this, and then add x1, y1 at the end. And then after that, you would take what's x2 plus y, x2 times y2 plus x2 times y3 plus x3 times y1. And then you would subtract y1 times x2, y2 times x3, and y3 times x1. So and then you take the absolute value of that just in case like your end result is negative, and then you get a positive number, and then you divide by 2. It's like looking back right here. So this is a formula. If you want to like copy it down quickly, I'll give you like maybe I don't know 10 seconds, 20 seconds to write it down. And then we'll look at how to apply shoelace on our specific problem. Shoelace in general is a pretty useful formula. It's especially useful if you want to chord bash something. Chord bashing is basically where you have a geometry problem that you're not maybe sure how to solve, right? So maybe it's like finding the area of this specific thing. So then you transpose that figure onto like a coordinate plane. Like for example, let's say I have a triangle that looks like this. And then like for maybe like there's a triangle that looks like this, and then maybe for some reason there's like a circle right here, right? Oh, oops, that's pretty bad. Something like this, right? And then you want to find the area of like this thing. It's like it might be difficult, or you might not know how to do this using like traditional geometry. So then what you would do is you would draw a coordinate plane. You would basically draw this figure and then find the endpoints, and then you can find this area. Although this is a pretty bad example since it's kind of hard to find parts of a circle using chord bashing, right? So then I'll assume that you're done copying it down, and now let's go back to our original problem. So remember that in our problem we're given 3 coordinates, right? So let me just like erase this stuff right here. So then we would list our coordinates like this. So let's start with 1, 3. Bit too close together actually. 1, then 3, 5, 1, 4, 4, and 1, 3. And then you would draw something like this, and then let's start chord bashing. Using shoelace. So first 1 times 1. What's 1 times 1? That's 1. Plus what's 5 times 4? That's 20. Plus what's 4 times 3? That's 12. By the way, this is 20, not a 26. And then we would subtract some stuff. So let me just like change this to like why not? So what's 3 times 5? That's 15. Okay. Minus what's 1 times 4? That's 4. What's 4 times 1? That's also 4. So in conclusion, we get 1 plus 20 plus 12. So that would give us 21. So that would give us 33. So we would then get 33 minus 23. 18 plus 4 plus 4, that's 23. 33 minus 23. So then we have 10, right? So remember at the end we still have to divide the area, this number by 2. So we then get that the area is 5. So that's reconfirming what we got the first time around. So our area is indeed 5. And then we take 5 over 30. And that's how we get 1/6. So does that make sense how we use shoelace? So the reason why it's called shoelace is because it kind of looks like when you tie shoelaces. Did someone say no? Does anyone want me to go over this again? All right. It looks like no one wants me to go over it again, so let's continue. So we have in the given figure, hexagon ABCDEF is equiangular. So we have this hexagon, and what it means by equiangular or equal angular is that all the angles are equal. So then that means that all angles are 120 degrees. We know this because all angles are equal, and the sum of all the angles in the hexagon has to be 720. So 720 divided by 6, that's 120. So then we also have ABJI and FEHG, sorry, that are squares whose areas 18 and 32 respectively. So we also have triangle JBK, which is equilateral, and FE, which is equal to BC. So what is the area of KBC? So we want to find the area of this triangle. So let's first establish some stuff. Yeah, so basically, Andrew is right. Equiangular means that all angles are equal, sides don't necessarily have to be equal. Like, you know, AB is not equal to FE because this is square, this is also square. And since this area is 18 and this area is 32, they have different side lengths. So first, let's look at some stuff. We know that this angle is 120. We know this because equiangular hexagon once again. We know this is 90 degrees. And we know that JBK is 60 degrees, or like this angle is 60. So what's 120 plus 90 plus 60? That's 270, right? So what angle is this angle right here? So let me just like draw in a lighter color. Light blue, why not? So what is this angle in light blue? This angle is actually 90 degrees, right? So that's pretty nice, right? So we know we know KBC, this triangle that we want to find the area of, is a 90-degree triangle. So all we have to do is find KB and BC, and then we'll have the base, we would have the height, and then we're done, right? So how do we find BK? Well, we can figure out the length of AB and like JB, right? Because IJBA is a square. So then JB is equal to square root 18. So we have JB equals square root 18. And since we know that JKB is an equilateral triangle, then KB, one of the sides we want to find, is also equal to root 18. And now what's BC? Well, we know that FE equals BC, right? So if we can find the length of FE, then we have BC, and then we're basically done, right? So what's the length of FE? Well, FE is the side length of a square. We know the area of the square, so then we can find FE. FE is equal to BC is equal to root 32. So in conclusion, we want to find what's root 32 times root 18 over 2. Base times height over 2, and then if you were to solve this, well, we would have like 2 to the 5th times 2 times 3 squared over 2, so that would give us square root 2 to the 6 times 3 squared, so that would give us 2 cubed, 8 times 3, 24, over 2, so that would give us 12. So our answer is 12. Does that make sense? How I approach this problem?
Yeah.
So first, if we have like KBC, then we want to find the area. We first find out that it's a right triangle, so that makes it significantly easier. Then we just have to find the base and height. We find the base and height by square rooting sides and equivalenting sides of the figure. So then we're done. All right. There are no questions, then let's look at problem 25. So in problem 25, we have a 1-inch squares are cut from this corner of this 5-inch square. So what is the area of the square inches of the largest square that can fit in the remaining space? So this problem is actually a little bit challenging. So what's the largest square that can fit in the remaining space? Well, I can think of a lot of squares that could fit in the remaining white space, right? So like, for example, this square, or like, that's a bad square, or maybe this square. But that's not necessarily the largest square, right? And Daphne has the right idea. So basically, she's saying that we should have a diagonal square. I believe she means something that looks like this. Yeah, this looks pretty bad. Oops. Yeah, this still looks bad. Sorry about that. Something that looks like this. Basically, you get the idea. A square that's diagonal that like takes up as much space as possible. And probably something that touches like these lines as well. So how do we find the area of such a square? Well, there are two ways we can approach this, right? So if we can find the side length of this hypothetical square, then we're done, right? Or alternatively, we can take the area of this large square, that's the one that has a side length of 5, this square, and then subtract the 4 triangles surrounding the smaller square. So there are two ways of approaching this. So we, of course, want to find the easiest method. So let's first do some drawing. So let's think about this triangle right here. Let me highlight it in green. So this is equal to 1. And let's say that, well, this is 1, this is 1. And let's say that this small length right here, this length from here to here, is equal to x. Well, that's nice and all. Then what's this length right here? If we can find this length, and if we can somehow set up an equation, then we're done, right? So what's this length? This length is equal to, it's equal to this length minus x. This is also equal to x. Like this equals to x, this equal to x, this equal to x, right? Good job, Alan. It's indeed 3 minus x. So you have 3 minus x right here. So we have x, right? So how do we find x? Well, notice how we have similar triangles. So let me just hide them in yellow. So we have this small triangle right here. And we have this large triangle, and you can tell they're similar, right? I don't have to explain why they're similar. It's like this angle equals this angle equals this angle, this angle equals this angle. You can tell by just looking that they're similar. So let's set up some similar triangle stuff, right? So we have x to 1 is equal to, it's like height to height is equal to base to base. So x to 1 is equal to 1 over 3 minus x. So yeah, we have this equation. Now let's cross multiply. We have 3x minus x squared equals 1. Yeah, this is pretty sad. So then we basically get that x squared minus 3x plus 1 equals 0. And then we can find x, and then we can either find this area, or we can find, we can find this area, and then we're basically done, right? So now all I have to do is solve for x. So we can just do not Pythagorean theorem, basic quadratic formula. So you have 3 plus minus 3 squared, 9 minus 4ac minus 4 times 1 minus 4 over 2a, so we would have 2. So 3 plus minus square root 5 over 2, right? And now you might think, but wait, isn't this like, and then we could like bash it out and then we'd be done, right? And now you might be thinking, is there an easier way to find x, or is there like another way we could solve this problem? So another way is that we could use the even larger similar triangle, so with base or like height 1 plus x and like base 4 minus x, and then we could just like find what's 1 plus x times 4 minus x, and then we'd also be done. So basically we just plug in x, solve, and then we're done, right? So I'm pretty sure you can all do the algebra on your own. It's pretty bashy. There are actually multiple ways of doing this, but ultimately you just find x and then you get on with life. So does anyone have any questions about the solution? I'm sure all of y'all can bash it out by yourselves. Okay, so it looks like no one has any questions, so then let's move on. Yeah, sorry. Give me like one moment to find. Yeah, so actually let me just like post the answer for y'all after class if y'all want it. When I upload the solution. Or sorry, when I upload the handout as well as like the recording. All right, so let's continue on to problem 22. So we have rectangle DEFA, and we have a 3x4 rectangle with DC equals CB equals BA. So now we want to find what the bat wings are. So I think we did a similar problem last week. I don't think it's exactly the same. Yeah, it was a pretty similar problem that like involved a similar configuration, but not the exact same problem. So the area of the bat wings, we can find it like this. So complementary areas, right? So what's the area of the whole rectangle ABCD? So that, sorry, DEFA actually, 12, 3x4. Minus all the area in white. So that would be like this triangle, this triangle, this triangle, and this triangle, right? So let me just like erase that since it's kind of distracting. So what's the area of DCE? And then we can multiply by 2 to get the area of BFA. So DCE, this is 1, this is 4, so then the area is 2. Multiplied by 2, so we get 4 again. And then minus, what's the area of CB? And then this point, like D, A, B, C, D, E, F, this point G, let's call it G. So what's the area of CBG? We're not exactly sure, right? Similarly, we can't be entirely sure of the area of EGF right now, because even though we know the base is 3, we don't know what the height is. So we can use similar triangles. So basically, if we were to draw the height, so the height, the total height between like CBG and GFE is 4. It's just like DE, the height of the rectangle. So then we apply similar triangles. The length of this height to this is equal to 1 to 3. So 4 divided by 1 plus 3. So that's 4 divided by 4. That's 1. So this height is 1. This height is 3. So then we can just get minus 1/2 minus 9/2. Does that make sense? And then we can find the area like that. So we just get 8 minus 10 over 2, 5, so 3. Does that make sense? And there's also an even faster 3 to 1, right? Because it's similar triangles. So if we were to look at this, right? CBG. So CBG has a 1/3 ratio to GEF. We know this because the ratio of CB to EF is 1 to 3. So the ratio of their bases is 1 to 3. So then the ratio of their lengths should be 1 to 3. The ratio of their height should also be 1 to 3, since they're cylinder triangles. Does that make sense? Yeah. There's also an even faster way of doing this. So basically what you do is you take CEF. It's basically the same thing, just slightly faster. So you take this area, CEF, and then you subtract like this triangle in white. So it'd be like CEF minus GEF. Same principle, height of CEF is 4. 4 times 3, 12, 6, minus, what's the area of GEF? That would also be 9 over 2. And then you take that area and multiply by 2 to get 3. Does that also make sense? Right. Yeah, the triangle I just drew, yeah, is half the area of the rectangle. That is indeed correct. It's just like same height, same base. You just have to divide by 2 because base times height divide by 2. So now let's look at problem 23 since no one has any questions. We have 2 congruent circles centered at A and B pass through each other's centers. And now you get to witness my amazing drawing skills. The lines containing both A and B is extended to intersect the circles at points C and D. So let me try my best to draw 2 congruent circles. Something like this. Their centers pass through each other's center. They pass through each other's centers. So center of triangle A, let's call it A. Center of triangle B, let's call it B. Amazing. And I just realized I've been calling it triangles. Okay, this is very sad. Okay, I meant circles. So the center of A is passed through by circle B, and same with like center B and like circle A. So the line containing A and B is extended to intersect the circles at points C and D. So the circles intersect at 2 points, one of which is E. So let me just like extend this line. So where C and D, let me just like circle intersect at 2 points. Okay, so I see so a circle, so 2 circles with their centers C and D. And then there are two circles intersecting at 2 points, one of which is E. So what's the degree measure of CED? Okay, so it turns out I am very blind. Okay, because I misread the problem again. All right. So let me see. So we have so let's extend this. It's a sad situation whenever you misread the problem. So it intersects the circles at C and D. And then we have point E right here, which is one of the intersections. So let me like draw this in like light green. So always make sure to carefully read the problem. Don't be like your teacher. So what is the degree measure of CED? Now this is a significantly easier problem. So let me actually do this. Let me connect EA and EB. Why is this? So remember last week when I was talking about properties of angles in a circle? So there's this property. So let's draw a circle like this, the center O, and let me draw this angle. This angle is like, let's call it 2 alpha. So then if I were to take this circle and like draw any line like this, so this angle is alpha, this angle is alpha, this angle is alpha. By the way, this is supposed to be intersect on the circle, not outside the circle. It's like something like this. So basically, as long as you have an arc and its corresponding angle, the angle that ends at the center is 2 alpha, and the angle that ends at the circle is alpha. So we can apply this, right? Let's look at arc EB. Yeah, alpha is generally what we call arbitrary angles. We generally name them like alpha, beta, so on and so forth, like, or theta, basically Greek alphabet letters, or Greek alphabet stuff. So what's angle EAB? Well, we actually know that angle EAB is 60 degrees. Why is this? Because A is the center of triangle A, so AB is equal to AE. Because AB is like the radius, AE is also the radius. So AE equals AB. Similarly, we have AB equals AB is equal to EB, since EB is the radius of circle B. So then we get AE is equal to AB is equal to EB. So this is in fact an equilateral triangle. So since so it might be confusing. So think of it like this. So we know that so let me redraw this using only this, right? So we have a point A right here. So AE is equal to EB. So we know this, it's equivalent right here. AE is equal to AB, and we know that EB equals AB, since symmetrical. So then we get that this is an equilateral triangle, so this is equal to 60 degrees. If this is equal to 60, then by properties of angles in circles, or angles inscribed in circles, then we get that this is equal to 60 divided by 2, so that's 30 degrees. So then if EDC is 30 degrees, then we also get like, this is also 30 degrees since it's like a reflective, since they're like congruent circles, right? So 30 and 30, so that's 60. So then can anyone tell me what angle CED is? Once again, to repeat, if we know that angle EDC is 30 and angle ECD is 30, then can anyone tell me what angle CED is? All right. We know that 120. Yeah, it is indeed equal to 120. It's just like 180 minus 30 minus 30, so that's 120. So the reason why we know that EDC is 30 degrees is because we know EAB is 60, so then EDC must be like half of that. That's like properties of inscribed angles in a circle. So since this is more like a problem series, I don't really have time to explain it in depth, but please, in your free time, you can always like Google inscribed angles of a circle, and then like there are lots of very cool properties about them. Very useful in problem solving as well. I highly recommend everyone to Google it on their own time, or like look at an AOPS textbook or something like that. Yeah, as Andrew said, the problem answer is C. So now let's look at problem 25. A semicircle is inscribed in an isosceles triangle with base 16 and height 15, so that the diameter of the semicircle is contained in the base of the triangle shown. What is the radius of the semicircle? So let's start with a few key things. So we know that the base is 16, right? And we know the height is 15, so let's draw the height. The height looks like this, 90 degrees right here. And now let's connect these two lines. So since the circle is tangent to the triangle right here, this is 90, this is also 90. And since it's a isosceles triangle, so then dropping the height will like bisect the base. So this is 8 and 8, just like 16 over 2. And we know that this entire length is 15. So if this length is 15, then let's think about a way in which we can solve this problem. So if this is 15, then can anyone tell me what this length is, like this side of the isosceles triangle using Pythag? $17, right? I'll remember last week I told you all to memorize like 8, 15, 17 triangles, like 3, 4, 5, 5, 12, 13, 7, 24, 25, all the important ones. Yeah, it's 17. Good job. So now, can anyone think of a clever way to find the area of the isosceles triangle using the radius? So let me give you a hint. So let me divide the isosceles triangle into two parts. So there's this triangle on the left-hand side. In this, we have a base, 17, right? We have a height. The height is radius r. So the area of this triangle, highlighted in light blue, is actually 17 times r divided by 2. And then we can like do the same thing on the other side. This is also 17, this is r. This area, the other area, is also 17 r over 2. And like Helena, sorry if I mispronounced your name. Helena suggested we can also find the area of the isosceles triangle by 8 times 15 over, or like just 8 times 15. It's like 16 times 15 over 2 is equal to 8 times 15. Yeah, but like it's okay. If you didn't immediately get it, sometimes you have to like solve a lot of problems to like see all the clever ways. So now we have this, right? 17r is equal to 8 times 15. And now we can just find what r is, right? It's like equal to 8 times 15, or 4 times 30 over 17. So 120 over 17. Oh, by the way, there isn't like a divide by 2, since you actually have like 17r over 2 plus 17r over 2 is equal to like 8 times 15. If you wanted to use 17r over 2, then you have to use like 17r over 2 is equal to 4 times 15. So that's like the easiest way of finding r. I'm pretty sure there are like harder ways, but like yeah. So that's like I think the best way in which you can find r. So does that solution make sense? Like how you can divide up a triangle and like find the area using other things? Like yeah, find the area of a triangle using like other heights and other bases. Okay, so looks like no one has any questions. So let's move on. So now we have problem 16. Choose D on line BC so that ACD and ABD have equal perimeters. What is the area of ABD? So all right, okay. So let's put point D here. So we know that ACD and ABD have equal perimeters. So what does this mean? This means that AC plus AD, AC3 plus AD plus whatchamacallit, right? CD is equal to AB, which is 4, plus DB, or plus AD plus DB. Also, please pay attention to what I'm saying in class, not who has whose name. Only name the person's name whose matter. Okay, sorry, I can no longer English. The only person whose name matters is my name, your benevolent overlord, teacher. Okay, so let's look at this, right? We have AD cancels out AD. So we have 3 plus CD is equal to 4 plus DB. So what does this mean? This basically means that CD is equal to 1 plus DB, or like CD is equal to 1 plus DB. So let's say that DB is equal to X, then this means that this is equal to 1 plus X. So this also tells us that X plus 1 is equal to 5, since like CD plus DB is equal to 5. So then we get 2x plus 1 equals 5, so then x equals 2. Yay! So that's very nice. So we get 2, and we have 3. So now we have 2 and 3. So now we want to find the area of ABD. So how do we find this area? Well, we know DB, right? So if we can find the height, then we're basically done, right? So let me just draw something like this. So we have the base, we want to find the height, and then we're done with the problem, right? So think about what I said last time. So let's call this height h. Can anyone think of a clever way where we can find the area of ABC and write it in terms of the height, right? Write it in terms of h. Yeah, also please pay attention to what I'm saying. Yeah, good job, Alpha. So basically, you take 5 h over 2. Andrew, that's not exactly what I had in mind, but I think I get your idea. So you basically find h using that, right? So you have 5h over 2 is equal to 3 times 4 over 2. So then we can find what h is. H is equal to 3 times 4 over 5. So Andrew, you were pretty close, or actually that you were a few steps ahead. So then we get h is equal to 3 times 4 over 5. So 12 over 5. So we have h is 12 over 5. So we have h, we have the base. So what's 12 over 5 times 2 over 1 over 2 equal to? So in short, yeah, 12 over 5, I think that's what people said. That's D. So we have height times base 2 over 2, and then we're done, right? Yay! So now we're done with this problem. Okay. So your benevolent dictator / overlord / teacher is done with this problem. So let's, so does anyone have any questions? So once again, as a reminder, it's pretty important to think of like different ways of how you can find the area. Okay, nice. So it looks like no one has any questions. So let's move on to problem 18. So problem 18 is pretty interesting. So in the convex quadrilateral ABCD, we have BCD is a right triangle. Sorry. Okay, I can no longer speak. BCD is a right angle. AB is equal to 12. BC equals 4. CD equals 3. And AD equals 13. So find the area of quadrilateral ABCD. So I actually want to ask you, is there a clever way where we could like add or subtract areas to get the area of ABCD? Because like I think the solution is pretty elegant and fun. It's just that I want y'all to like see it by yourselves. Because I don't want to spoil the fun of every problem by like giving you the answer or like giving you the solution on a plate. So let's see. Can anyone think of a way where we could like add or subtract areas? So ABD minus BCD sounds really promising, right? Or looks really promising. So what Helena, I believe, wants us to do is connect BDB, right? This problem is just like begging us to like connect DB. So we know that this is a right angle, right? DCB is a right angle. So then we have like 3, 4, 5 triangle, right? We have 3, we have 4, we have a right angle. This is 5. And now you'll be like, wait a minute. We have a 5, 12, 13 triangle. Huh. That sounds a lot like a certain right triangle, right? So then we can basically say, oh, this is a right angle. And then we're basically done, right? We have like ABD, we have DCB, we can subtract their areas and then we're done. So what's 5 times, so what's the area of ABD? Well, that's like 5 times 12 over 2, so that's 30 minus, yeah, Alan is correct. 3 times 4 over 2, good job, Alan. Minus 6 is equal to 24, and good job, Alpha, as well. So then we get 24. Yeah. So that's how you do a problem like this. So if you ever see a problem where it's like begging you to connect a line, or like you see some lines that can be connected, then do it. All right, so does anyone have any questions about this? So as you do more problems, then you get like, then you form some sort of intuition that, oh, I see a figure that looks like this, connect DB. All right, so now let's look at problem 22. We have a right triangle ABC. AC equals 12, BC equals 5, and angle C is a right angle. A semicircle is inscribed in the triangle as shown. What is the radius of the semicircle? So we have an inscribed semicircle, right? So we know that like, let's call the center of the semicircle, which is on this O. Okay, so if this is O, then let's connect the tangent point to O. So this gives us a 90 degrees angle, right? Okay. Basically, you have a semicircle inscribed in a triangle. We want to find R, the radius of the semicircle. So remember the couple problems from before where we like use clever ways of finding like the area for like a height that we wanted to determine, right? So remember this problem, right? Where we had a similar problem-ish, where we have like a radius r. We use an alternative way using r to find the area of the triangle. So that's exactly what we'll do here. So let me just like zoom in a lot so it's easier to draw, and like switch to like a light green. Why not? Light green is my favorite color. And let's draw OB. All right. Let's pause for a moment. This is R, this is R. So can anyone tell me a rather clever way where we can find the area of ABC and write that area in terms of R? So the idea is that we have like three triangles, right? So this triangle that I'm like highlighting with my mouse right here, we can find the base. The base is AB, that's equal to 13, right? We have a 5, 12 triangle, it's 13. Oh, we know that this 90 degrees, we're given that. So AB is 13. So we can find the area of ABO, that's 13R over 2. And we also can find the area of BOC, that's like height 5, base R, 5R over 2. And now, can we find the area of ABC normally? Well, we have 12, we have 5, we have the base, we have the height, then we're basically done, right? So let's write area of ABC in terms of R. So once again, we have 13R over 2 plus 5R over 2. This is equal to base times height over 2, 12 times 5 over 2, that's equal to 30. So then we get 18R over 2, that's 9R is equal to 30. So then we get that R is equal to 10 over 3. So does that make sense? How we once again use an alternative form or an alternative method of finding the area of a triangle using radius r. It's like we did a similar thing, albeit easier, a few problems ago. All right, nice. And now let's look at problem 25. In the figure shown, we have US and UT and line segments of 2. And then we have measure TUS is equal to 60. So we have arc TR and arc SR are each 1/6 of a circle with radius 2. What is the area of the region shown? So let's think for a moment. So let's think for a moment. Remember the question a couple problems ago that looked like this, where we have like connected this line and then like every piece of the puzzle kind of fell together and we could solve it? Well, could anyone think of a way where we can extend a couple lines, or maybe a few lines actually, and we can find a really, really easy like complementary area? Right, SR and R, SR and RT. So basically the idea is, let's continue this line like this, and let's continue this line like this. And now let's draw this. And you might say like, well, what's the point? We don't know this angle, we don't know this angle. How do we find, this doesn't give us anything useful. This might as well be like 59, and this might as well be like 15, or like whatever 180 minus 60 minus 59 is, or 61 actually. However, we're given something interesting. So we know first of all that TUS is 60. So the sum of these two has to be 120. And alpha has got it. So we know that arcs TR and SR are each 1/6 of a circle. So what's 360 divided by 6, right? So if I were to continue this, right? Let me just like draw a circle like this, draw a circle like this, right? So what does this give us? 1/6 of a circle, 360 divided by 6. So this is equal to 60. This is also equal to 60. So now this is all coming together, right? So we can find this area. So if we can find the area of the equilateral triangle and then we subtract like the two pizza slices or like the two slices of the circle, then we're done, right? So now let's first find this length. So we know that the radius is 2, right? So 2, 2, 2, 2. So side length of the equilateral triangle is 4. So let me actually so how do you find the area of the equilateral triangle using the sides? So there's this like s squared root 3 over 4, I'm pretty sure. Yeah, should be s squared root 3 over 4. So basically you have like s over 2, s root 3 over 2. It's like s root 3 over 2 times 2 over 2. So basically, if we have s where s is side length of an equilateral triangle, then the area of the equilateral triangle is s squared root 3 over 4. So let's apply this formula, right? So the side length is 4, so we have 16, 4 squared root 3 over 4. So the area of the triangle is 4 root 3. So we have 4 root 3, right? That's the area of the triangle. And then we want to subtract these two pizza slices, right? So let me just like change this to like a light blue. Why not? So how do I find this area? Well, like the area highlighted in blue. Well, that's equal to like 1/6 of the circle, right? So the area of the circle is pi r squared. That's like 4 pi, right? What's 4 pi over 6? 4 pi over 6 is, well, 4 pi over 6, that's like this, right? And then this is also like 4 pi over 6. That's symmetrical. So 4 pi over 6 times 2, so that would give us 4 pi over 3. So Andrew is indeed right. It's B. So it's 4 root 3 minus 4 pi over 3. So that's it, right? So now we're done with this problem. It's 1:30, by the way. So that's basically the end of class, unless y'all want to do like one last problem, since it will be the last time we'll meet. In this class, at least. Sure, one more. All right? Okay, so do an accent. Okay, sure. For my amazing students, okay, I'm from Texas, so I'm already doing a Southern accent. But sure, okay. All right. In the diagram below, a diameter of each of two smaller circles is a radius of the larger circle. If the two smaller circles have a combined area of 1 square unit, then what is the area of the shaded region in square units? So let's start with this problem. We first have diameter of two smaller circles. Let's draw it out like this, like so. So now y'all behave in the chat. All right. If the two smaller circles have a combined area of 1 square unit, then what's the area of the shaded region in square units? Well, we do know that, let's say that this area, well, the radius of this is r. So we have that this length is r. So then we know that the radius is 2r. Okay, yeah. So the radius of the large circle is 2r. So we have that r squared, pi r squared times 2. 2 pi r squared is equal to 1. So we also have 2r. So the radius of the large circle is 2r. So then we have pi r squared, 4 pi r squared actually. So 4 pi r squared is equal to 2 pi r squared. 2 times 2 pi r squared. So that gives us 2 times 1. So that gives us 2. But we're not quite done yet. So we know the area of the large circle, but we want to find the area of the shaded region. So that would be 2 minus 1, since that's the area of the large circle, minus the two smaller circles. So that gives us an answer of 1. Okay, so now we're done, right? That was also terrible. Okay, so we're done with problem 15, right? So now it's 1:33. That's the end of class. So I've had a really fun time teaching y'all. So that's the end of like our AMC8 problem series. It's very sad seeing y'all go. So yeah. So yeah, thank you all for being such amazing students. Yeah. Goodbye. Bye bye. Farewell. Adios.
Bye. Thank you.